Okay, it's started recording.
Is it done?
Yeah.
I haven't got the notice.
Yes, it says it is recording.
No, I haven't got the notice, huh?
You haven't, okay?
I got it.
You got it? Okay.
Okay,
All
so
right.
shall we start?
I'm ready.
Fine, I got that. Great.
Okay, thank
Good.
you. All right,
All right,
guys.
sir, you can go ahead.
Thanks, sir. Thanks. Yeah, let's do that.
Okay, thank you, guys. Really good to see you all, at least the ones I can see. And so, it's been a while since I worked on this, but it doesn't seem to lose its relevance. Last week, if you read the newspapers here, we had an $11 billion program for Mars sample return that they essentially canceled. And now they're going to go private with that. And there's lots of controversy around that. And so I'm going to talk to you about, how Mars missions came about and so relevance of the work we did and why it's considered one of the pivotal, missions of NASA. And so absolutely stop me along the way, or if you want to have questions later, that's fine. So let's talk about this. So Mars, so let's at least learn a little bit about planets first. So sort of gives you a sense of how far things are, how complicated things are. If you look at where Earth is and where Mars is and where the rest of the stuff is, you realize that really there's not a lot of places we can go easily. If you look at the, hey Sanjay, good to see you. And then, so as you know, the first, okay. So as you know, the very first planet is Mercury. It's very close to, and then the temperatures are really awful. And of course, then there's Venus, and then there's Mars, and then on and on. And you can see that if you look at that line, there really isn't a lot of places you can go except Mars. Mars is a lot like us and has a very interesting geology. There were oceans there. There may have been volcanoes there. Definitely were oceans there. There's lots and lots of water still there and sort of under the surface. And it actually has a good atmosphere as well. So it is something actually we can live on if you had to. There are places that are actually warmer than Earth. So this thing keeps moving for some reason. The other thing is that it actually uh, is not that far from us in a relative sense. You can sort of get there within 6-7 months. Although, because it goes around the sun every 2 years, 2 Earth years roughly, you get too close to it only 2 years or so apart. So as a result, what happens is that if you want to go there, you really have this kind of a window that shows up every 2 years. Otherwise, it takes a very long time to get there. So typical travel times will also tell you why it's very, very hard to go to, sorry, it keeps flipping back, go to the outer planets. Moreover, Jupiter, Saturn, Uranus, Neptune are all gaseous planets. And so even if you got there, there's not a place to sit. And really, if anything, we'll probably go to one of the moons of Jupiter or moons of Saturn. Jupiter has 99 or some moons, and they're pretty large. And so it's very unlikely that we would have any other place in this particular solar system that we would actually want to land and do anything. And so Mars has always been of interest. And the distance is going to let you know that really there is not much else we can do except to go to Mars, of course, beyond the moon. And I've added sun and the moon over here. And AU is about 93 million miles, about 150 kilometers. So you can get a sense of how far things really are. And this diagram is particularly interesting because it shows you relative to where Mars is, where everything else is. And it's exceedingly difficult to get to these planets, and therefore we don't go very often. Pluto, for example, goes around the sun every 250 years. So these things are beyond human scale, even if you wanted to kind of do anything meaningful there.
This must be an old slide, Rajiv. Pluto is to the planet?
It's to me. Yeah. So going forward, before 1996, there were 28 missions to Mars. and they were all done by either Soviet Union, Russia, or by the Americans. Americans did only 10 missions, out of which 7 times they made it successfully. And Russians pretty much never did. Even though they have these so-called partially successful missions, they never had a lander that landed on Mars. They had a few orbiters that made it. And but they tried sending rovers. They were very ambitious. And sadly, their last mission, which was 96, which was supposed to compete with the one that we had sent, had a launch failure. So the interest in Mars is always around. There are basically, if you look at the types of missions, they're typically flybys, orbiters, rovers, and penetrators. So penetrators is sort of more of a unique thing for Soviets. But so flybys are, you just fly by a planet, takes a lot of pictures and go away. Orbiter is where you actually, somehow get caught on the gravity and then create an orbit around that. It's very complicated to do that because think about it, you want to go as fast as possible to get somewhere and then slow down. And there's not much there except to be pulled by the gravity. And of course, you need propulsion to basically create a long ellipse and then slowly, round that ellipse out. And of course, the holy grail is to land there and be able to survive the landing. And landing is not easy. That's why it was very difficult to land. So this is sort of gives you a sense of how difficult it was to get there, but not for lack of trying. There's another really important part about going to any planet or any place in space, and that is the so-called propagation delay or the circuit delay or communication.
Rajiv, a quick question. So, I mean, it's if you go back to the previous slide, I think of the Russians and US now, including SpaceX, etc., having good rocket technology. So launch failure is a surprising failure mechanism. So what exactly was fail? I mean, they just failed to launch from Earth to get to anywhere?
Well, in 60s, there were lots of launch failures.
Yeah. No, I'm talking about I look at the
Yes.
late 96 one.
Right. So that's another point. So remember, there is a difference between what SpaceX is doing now or many launches that we do routinely now, and those are to low Earth orbits. You're popping a satellite and that's it. Getting away from the gravity or gravitational field of Earth requires a very different kind of rocket and different kind of propulsion. So you typically want to get much further away. So it takes a lot more complex, technology, and therefore, if you look at, in the lunar mission days, we lost a lot of launch rockets then also. So deep space, missions are very difficult.
No, I get that. I get that, and I see all
With
the
heavier, bigger rockets, and so and part of the problem is that I think Soviet launch technology was never really. I mean, they have lots of great rockets. Don't get me wrong, but I think it was one of the early eras where we also lost lots of them. We just don't show them. Just we didn't lose many going to Mars. I guess that's what it says.
Yeah, what interesting is because they did have successful moon missions, right? I mean, it's not like they
Yeah,
didn't know
no,
how to get out.
they eventually had successful Mars missions also, but I think it has to do with how you really put together these rockets. So, we also had a lot of military missions at the time. Like the one we used was a Delta rocket, which is actually built for the Space Force program. So there was a lot of other technologies they were supporting. So basically, it has to do more with how frequently and how they develop the rocket technology. But
Thank you. Thank you.
so another really important thing to keep in mind when going anywhere is the propagation delay. And what that is how long does it take for, one bit to traverse from one end to the other? And when you are, say, on Mars, like here, and a rover needs to talk to something on the Earth, you have this deep space network on Earth where we have these 3 large antennas about 120 degrees apart. One's in California here, and one's in Spain, and one's in Canberra, Australia. And as the Earth rotates, we always have something pointing towards everywhere. And so usually the way most of these spacecrafts or most of these landers talk back to the Earth is to actually the rover or lander talks to the orbiter then talks to the through a direct link to Earth. Now, it's not like you're constantly talking though, right? Because remember, orbiter is going round too. Typically what we call there is a daily window, how much time the rover or lander gets to talk to the orbiter, and then orbiter in turn talks to Earth. So typically in a day, on Mars at least, with about 2 or 3 orbiters we have, now we have 3 orbiters. And of course, you can use sort of each of those orbiters to use sometimes the Mars Express, which is a European orbiter. And so we get about 8 minutes in a sol. Sol is a name for the day, on Mars. So you only get 8 minutes a day. And the bandwidth is about 2 megabits per second these days. And of course, the bit rate from orbiter to here on ground is about 32 kilobits per second. Compare that to the moon, we now have a direct laser link to the moon, and we can actually get almost 700 megabits per second, with a 1 second delay. So we can stream video from the moon, but still it's about 1.3 seconds away. Now, this is a really important part because if you think about these delays, what it tells you is that you really cannot control anything remotely from here. So if you want to sort of move something, you would say go, and then you'll find out maybe 20 minutes later, it's a go. Then let's say it moves and it wants to send back something, it'll be another 20 minutes, right? So it'll be 40 minutes after that you'll find out. So there's no closed loop thing you can have, and that is only if you have the direct connection, but you don't, right? So for most of the time, you really don't have connection with your spacecraft. So what that does is that you actually have to have autonomous system on the other side. Or sometimes people call it tele-autonomous system because you're sort of directing it where to go, but it's really not something where you can sort of drive sitting here because of this communication delay. And this also makes it very hard to go to other places, particularly Mars and further, because think about it, you have to kind of basically program the robot or even your spacecraft to go, and then it has to find its way into the planet, on a programmed trajectory. If there are any variations, something happens, you're not going to find out for minutes, if not hours. The further out you go, the more time it takes. So as a result, and with very limited bandwidths and also very limited windows through the day, you really don't have a lot of chance of doing any kind of direct communication with any of the spacecrafts. And this is one of the hardest parts of going somewhere. And that's one of the reasons why many times missions fail because you really don't know when it's getting closer, if the last minute, you can do that when, let's say, we're making re-entry into the Earth, you actually can, not that you can do much once it's coming in at 7,000-8,000 miles, miles a second, you really can't do much. But the point is that you really have to consider this as probably the biggest problem why it's so hard to do anything that far away. Okay, so you're right about that, Sanjay, that one part is to get off the Earth and then go into deep space, which means you have to break away from the gravitational pull, and then traverse this long distances, lots of trajectories, and then get captured by this planet. Of course, you typically use a gravity assist if you want to speed up or if you want to slow down. And then you have to create like a long ellipse, and then you slowly sort of make the ellipse rounder and rounder and get closer. And then I have to enter the atmosphere of that planet. If it's a planet, moon doesn't have an atmosphere, as you know. And then you have to slowly or somehow land at hopefully 0 meters per second if you land on a hard surface. So it's a complicated affair, especially if you have no communication, right? So one thing is certain, that you needed a way to autonomously get there. Now, as I said before, there were only 2 successful landers prior to this. One was Viking 1, the other was Viking 2, both American, and of course, those were in 75. So 1975, we were all pretty young then, and we all know about Viking. And but as you know, if you land at 2+ spots on a planet, you're really not going to know much about the planet. You learn a little bit, but not a lot. And so ideally, you want to be able to move around the planet and actually take samples from all over the place. The other thing is that typically, and it's kind of a colloquial, saying in space business, is that places that are interesting to land are not interesting to see, and places interesting to see are usually not interesting to land. That probably is true almost anywhere. But the point is that if you wanted to get on some kind of a like a lakes, where the rivers may have been or so on, the surfaces are not that good, or maybe more complex to land. So typically you land in areas that are more like deserts or such, and then you want to walk away, go somewhere else. So you'll see that most of the landing sites tend to be relatively simple to land, and then from there you want to move. So for all these things, what it suggests is that you have to have a robot. Plus, because of this propagation delay, it needs to be autonomous. So we knew this long ago, and therefore we basically stopped.
Sorry, Rajiv, some more questions just
Yeah,
started.
sure.
So do we have, again, as you were talking about autonomous and stuff like that, it's of course, there's no GPS network available on Mars, but so it must be visual kind of tracking it's doing on its own to move around, etc. I'm imagining, but I'm also thinking, how well do we have the Mars planet mapped out through the orbiters to say, okay, we can look at the field of view of any of these robots and kind of say, it's here.
Okay. So jumping ahead a little bit, we'll get to
Okay, so I'll wait then.
Yeah, okay. So part of it is that we do have a reasonably good idea about the terrain of Mars because of orbiters that we've sent over the years, ours and other people, other countries and all that stuff. We have a fairly good map of Mars. The resolution is, of course, not quite like what we have here on the Earth, but it's fairly good. So we do know, what are the interesting areas. We have aerial imagery. As you know, aerial imagery is pretty good these days, but now we're talking about 90s. And so the compute was very different in those days than it is today. And so, but we have fairly good idea about the remote, at least remotely mappable geology. But that resolution is not good enough to navigate. And of course, navigating when you don't have the maps is a different kind of navigation. But we all do that. You go into a hiking trail. There's no map, and you find your way because you can see things, right? So that's really the next point. So how do you go that far away, and then you autonomously move? But one thing I hope you agree that we have to have autonomous robot on the other side, and that's really what most of this presentation is about. And that's what was keeping us from going more often, because what's the point of going if you don't know how to drive, right? So autonomous driving in those days, I'm talking about 80s and 90s, and so, very early 90s, was basically based on, AI at that time. We'll look at that. And the way autonomous driving used to work, and there was the paradigm was like this, that you basically sense your area. So you have to stereo vision. You take an image of the terrain. That's a very typical sort of martial terrain where you would land, and then you would map that out. Then you would model it. So you'd model the terrain, you create obstacles and all this stuff. You map the terrain in a certain way. You figure out what's the best path is, and then you create a plan. You generate a plan to move the robot within that terrain, and then you act on that plan, and then you move the robot. So what's the problem with this? This is 1990s. It takes hours and hours to do this, right?
Too much compute.
Because you don't have much compute power. Secondly, as soon as you move, the world changes, right? So if you move 2 meters, everything changes. You move 10 meters, literally, you may as well just map the whole thing again. Now, today, we don't think of much of it because we actually process things very, very fast. But in those days, an image would take, sometimes 15, 20 minutes to process. These algorithms for creating these terrain maps and terrains would take hours. And so the idea was that, but the basic idea seemed right. And if you think about it, you say, well, how do you do things, Elsa? And you say, well, you just like you said, you look at things and you find your way through it. And that was kind of the going paradigm in AI. And it was called sense, but sometimes called sense plan act. A model is sort of part of sensing. So sense model plan act was kind of the going paradigm. And it seemed like the right thing to do. And basically the expectation was that over a period of time, our modeling will improve, our planning will improve, and eventually we'll be able to do this. So we basically started building robots here that will be able to do that. So in the late 70s and early 80s, there was a robot called the Blue Rover. It was built in this is back of Jet Propulsion Labs in Pasadena, and it was originally developed as a moon rover. It's got this kind of a little hingy thing. You can see a little over here, and it allows it to do that, and you can basically chain it up, and it goes over things relatively simply. This is a very simple robot. It basically is remote driven. Remember, on the moon, it's a 1.3-second delay. You can more or less manage it. More than 2-second delay, humans start having problems. So 1.3 second maybe is okay. So we basically had this robot lying around and said, could we take something like this, which basically goes over things pretty well, and convert it into an autonomous robot? And so that's kind of where the thing started. So in late 80s, the systems group in JPL basically came up with this. Now this is it's a big robot. I think one of the funniest things about this is the monitor that's sitting on top of that. So it's a test bed. It has a stereo machine vision, so it has several cameras at the top. This big cabinet you see here is really a cabinet of computers. Remember, the fastest computer you could buy in 1990s was probably about 100 megahertz. I think even that would be too much. It was a 8386. So long before we had basically it was a DOS world. And really you had to, and then of course there was a Spark station, which was also, so you could do some stuff like that. But basically the idea was that we would take a picture and then would create a model of the terrain. And we could actually, and so this thing required a whole power plant in the back to move. So sorry about that. Okay, so we got a power plant to move. It had a cooling system even because, as you can imagine, this is so large. But basically, you could do some autonomous driving. In 1990s, we actually had what they used to call it this was a test bed. And we drove about 100 meters in 4.5 hours, give or take, right? And that was quite unique. Nobody had done that before. And without anybody telling you, just go there, and then it just goes 100 meters and avoids everything and figures out how to go and so on and so forth. With very little, in today's age, very, very little compute power. And but it was a complex approach. There's a very small other thing that you have to worry about when you go to space, and that is the launch cost. In those days, deep space launches were costing $50,000 to $100,000, sometimes even more than that per kilogram. This thing weighed 2 tons. And some of these, you're not just going to send the robot, you'll send instrumentation with it. Now, if you put instrumentation in it, you have to also launch it. So there's the weight of, every time you increase the weight, you actually weight the increase of amount of propulsion needed. So that weight gets added. It's kind of a bad sort of additive kind of process. So in the end, what happens is that a mission like this would take $2-3 billion to get off the ground. And there just wasn't $2-3 billion in 90s any time to do this kind of mission. And so another constraint that happens is that, hi Dharam, so the problem was that you really, even if you could build this, and even if you could go like this, could you really have would you really have the money to do this? Would you really have and frankly, if you bring something this big, also you have to land it. So that means that you also need massive rockets to land it. I'm gonna mute this guy. Okay, so you would have to land this on another planet, and of course that means you need bigger propulsions. The more weight is generally more problem. So even though we sort of knew how to navigate and we sort of figured out how to do this, we really were kind of wondering if this was ever going to take off. And there was general expectation that over time, computing will get more and cheaper, and of course, you would have smaller, more compact systems. But really, it was anybody's guess. So we thought maybe 10, 15 years will we go there. So generally, the target was for a return for a mission called MRSR, Mars Rover Sample Return, to be launched around 2004, 2005. And then, of course, as you know, we haven't actually gotten sample return part done even now. We're in 2024. So with this sort of in front of us, a lot of us started thinking that, are we really thinking about this correctly? Is this really the only way to navigate autonomously? Are we really sort of relying on this kind of natural instinct that we had, that we look at things and we find ways and we go, this seems very obvious, but is that really the right way to look at these things? So we started looking, and some of had been researching something different. And so, is there an alternate approach to navigating? And that's kind of what, we had a small group, and there was a research paper written by you muted me, whoever did that. Sorry. Okay. So there's a research paper in 1989 by Rod Brooks and Anita Flynn at MIT about a concept of behavior control. And we were sort of investigating, how do these creatures that are tiny creatures that get around and navigate really quite well autonomously? They don't really need a lot. They don't even have eyes in many cases. And they do fine, right? And they don't have a lot of compute power, we know. So how is it that they're doing it? In fact, if you think about it, all of us constantly are computing. Even when you stand up, there's all kind of actuators going off and on. So how are we doing this? We're obviously not consuming that much power to compute. We're not using eyes. We're not using this. So how are we doing this? And so this was a bold idea at the time, saying that really this sense, model, plan, act is not a good paradigm. Maybe it's actually the incorrect paradigm. And so that's really where we looked next. So we looked at little bugs. And it's more, for example, there are other ways to look at this and say, there's a cockroach right there. How does a cockroach move? Let's say it's approaching an obstacle, or it doesn't know it's an obstacle, actually, it just sort of keeps moving towards a corner or something. It doesn't really know, it's probably smelling something, and it moves towards that. And its tentacles are going all over the place, it's doing this, right? And it maybe touches a wall, maybe it touches something in there, and you can see that they kind of move their tentacles around like that, right? And so it feels the walls, and if it finds a path, it just goes through, right? It doesn't really think all that much about what it's doing. It just kind of keeps going through toward a goal where the smell is increasing, something like that, right? Another thing it can do is it can turn around because it says, oh, nothing there. It just gets tired, it turns around, goes back. So that's another sort of behavior that it has. Or it sometimes goes around things. So we were thinking about this and saying, wait a minute, isn't that exactly what we do too? If you walk through a crowded area, you got all these sensors going on in your body, right? You've got your balancing and all this stuff going on. And your eyes sort of are looking at things, but they're really looking at a very low resolution, and just sort of spotting things. So you look at it, you aggregate stuff, you kind of cluster things and say, okay, well, there's a pathway. You basically do only three things. You either go through, or you go around, or you go over, right? So if you walk around and next time you go for a walk, just think about it. What do you really do? You just keep walking, right? You're listening to music, maybe you're talking to somebody, you're quite engaged in that. What are you really doing, right? You're really basically going through things that you can go through. You're going around things that you have to go around because you can't go through them. Or you just say, I can't go anymore. And then you kind of engage your sensors. You say, oh, what are you going to do here? And you're going to make a decision, you plan, and you go around. Now, the moment you do this, you discover that you don't need a lot of computing. You need very, very simple, so almost binary sensors, and you can do these things all day long. So because of that, we realized that, and this is kind of what the behavior control is about, and says that sensory inputs trigger behaviors. And these behaviors are acquired in the case of various creatures, genetically, or just that's the design of that creature. And if you're kind of a lower, simpler organism, it's a hardwired behaviors. They don't really improve much. This is exactly how they are. And therefore, many of them will just keep trying and then eventually die because they don't know any better. You can see sometimes a bug is stuck and it doesn't know any better. It just keeps hitting it and dies, right? Others have more tunable behaviors, right? So the behaviors are basically the software is there, the hardware is there, and they can do it, but they can improve it. If they lose a leg, they start to learn how to walk with 5. If they have a slightly broken antenna, they compensate by the other. So they actually have ability to tune their behaviors a little bit. So a little bit hybrid organisms. And if you want to call them intelligent organisms or more elevated organism in some way, they can actually not only tune their behaviors really intensely, but they can actually sequence them. And more importantly, they can acquire new behaviors. But what they're doing is they're acquiring these behaviors and they're only thinking in terms of these behaviors. So another way to think about this. Let's say you want to go from Los Angeles to San Francisco. You don't actually start computing, well, I'll go 30 centimeters this way and then 47 centimeters this way, and then I'll go up half a degree and so on. You'll never get there. So what do you really do? You say, well, I get on the street and that street and that street. And then you're sort of reliant upon the behavior of that body that's moving, person in a car, to figure out how the local stuff works, because the local conditions are constantly changing. So you can just sort of say, well, turn at the next right. And then you go to the light's not working, right? So you figure out and you're going to make another plan if necessary. But until then, you just keep following. And in a sense, you have these higher level objectives that you follow. And in between, what you're really doing is you're really relying upon these behaviors. Think about the way you walk, think about the way you sit, think about the way you really act in your environment. More or less, you're just a collection of behaviors. And these behaviors are sometimes genetically acquired, sometimes, of course, in case of robots, they're programmed, and they can be learned, right? So we've built robots that we can start out with absolutely no understanding of walking. And then they, through sort of definition of a pain, like let's say they fall, it's a pain, they actually very quickly, in a matter of minutes sometimes, learn how to walk. They walk quite funny, but they do walk, right? So you can actually generate behaviors also very simply. But what's the key idea here? The key idea here is that you can actually build these things with very, very, very simple compute power. So we looked at this and we said, what if we build one, test this idea out? By this time at MIT, a couple of people were already building a bunch of little robots. One of them was the student of Rod, who became an intern in 91. And so this all sort of ideas started coming in 90s because we were looking at the other one, and it was kind of slow. So while we kept going with that one, we had our intern, who was Colin Engel, who eventually became the CEO of iRobot many, many years later. Anyway, that's just for more. So, and of course, so we had this kind of a team put together and we said, we'll do the software, you do this, and we build this robot. So to do that, we decided to build the first robot, which is an autonomous robot. It's called the Tooth. And it had a single processor in it. That's the processor. It's a Motorola 6811, 2 megahertz. We sort of underclocked a little bit, but it was 2 megahertz, and has 16 kilobytes of RAM, and really not much else. Has about 16 bits of I/O, and so we could control, up to 8 motors, let's say, and or 8 devices, and it had a few sensors. Right up on top, you see there's so I'm going to turn this thing on, and you can hear what it does.
You are looking at Tooth, the first micro rover developed at JPL. This robot was an indoor test bed used to develop the autonomous control software. This software technology, called behavior control, allows robots to operate autonomously using very small computers and very simple sensors. Tooth's microcomputer has only 4 kilobytes of memory, yet Tooth can reliably perform complex tasks without any human guidance. In this case, the robot has been programmed to find small objects and deposit them next to a light bulb beacon. The robot uses infrared proximity sensors and contact sensors to detect obstacles and find objects for retrieval. For the return, it uses photodetectors to find the light bulb.
So now, of course, sitting in 2024, this seems like nothing, but in 1990, this was earth-shaking. You know, you could actually build robots that could run all day long and keep doing autonomous things. You know, they would be able to, I mean, you could take this as like if it was a vacuum cleaner, this would keep running all day, right? So you could actually make it go to a light. You could, so that's kind of like a mission. Hey, go there or go here. And you've given it an objective that says, pick up anything that size and then do this at the end of that mission. That's it, right? So with very simple sensors, with very simple behaviors, we were able to, and this thing had about 8 or 10 little behaviors, you could actually achieve fairly important things. But now the next question is, well, that's great inside, you got a level, level thing. How do you really translate this to a natural terrain, right? That's a good question. This is not natural terrain. And of course, nothing like on Mars looks like this. So how would you build something like this? What would a behavior mean, in a natural terrain? So
You are looking.
okay. So we'll go to, so again, in 60s and then later on in 80s, there was a concept called, and this is Rocky one at the top, but basically we wanted to build a idea of like, can we build things that, as I said, can go over many things, go through most things, and then go around other things, right? That's the basic idea. But natural terrain, that's a little hard to define, right? I mean, if you have lots and lots of rocks, I mean, what is going through something? What is going over stuff? So there was a passive suspension system called rocker bogie. It's a little bit like, you know how a tank has all these little, as a chain, and it kind of goes over one side and the other side stays. So one side can go over something, but the other one stays. So you can actually maintain grip on the surface while you're moving. And it can really do amazing things. Generally, the goal is that it should be able to go over things that are at least the size of your tires. And this thing very remarkably does that very well. And so we took this rocker bogie, which is a mechanical system, and then said that the design had been around for a while. And we said, what if we added our smarts to it, which is one computer, basically, again, made out of the same processor that I have here, 6811. Okay. So we built this, we put some motors to steer it, and it said, we can see if this can go over, and you can see that it shows that it's going over a rock that's a lot bigger than its wheel, and said, can we test this in the field and prove that if we had something like this, we could go over most of the terrain. And if it's that big, we could probably detect it and say, go around it, right? So that was kind of the idea. So next thing came this, and I'm going to turn this on.
This is Rocky 1, an outdoor robot built to test a revolutionary mobility system called a rocker bogie. The rocker bogie is a 6-wheel springless passive suspension system developed at JPL. This advanced mechanical design allows the robot to scale obstacles which are larger than the robot's wheels, and often larger than the robot itself.
Right. So look at that image there. How many cars can do that? How many systems can do that, right? So, but you notice that even with a massive obstacle on one side, it decided to keep going. So that means that it sort of felt that I can do this. If you look at sometimes little bugs, they'll kind of go like this, they kind of move their leg and go up like that. So they kind of sense it and say, I think I can make it, unless they got to flip over and then they go back, right? So that was kind of the idea that we said, if we could just sort of sense it like this, that says, I can go over most things. So I'm going to try. And if I feel like I'm going to use some inclinometers or something, which are really binary sensors, sort of analog sensors, but the linear sensors, they can say, well, if I'm going to tip over, then I'm going to go back. Otherwise, I just keep going, right? And given that I got 6 wheels, I should be able to detect that I'm going to go over long before I actually go over, right? So that gives a lot of mobility, and of course also some sensible decision-making ability to say, hey, I've got an obstacle on the left, I've got an obstacle on the right, I got obstacle in the front, and this thing could go up good 35, 40, 50 degrees. So basically more than 100% grade, and then make a decision and say, oh, maybe I shouldn't go and go back. So next thing was to test this much more extensively. So we took this into natural terrain. And so you can see this was kept together. That's a very old Macintosh. And on the right, left is a camera. That's my family's camera. Stuck it on top just to look at things and a few things here and there. And then we basically started testing it in the field. And this is a test that was done in Mojave Desert. There's a place called Mars Hill in Mojave. I hope the video will load. There's some really old videos. All right, for some reason it's not loading. Okay, we'll go to the next one then. It's just, okay. Believe me that it actually did some testing in the field. So we went to Mojave and we tried it all kinds of places. Even with the wheel stuck in one, it always comes out. Because the next thing is anybody would say, well, that's all great, Rajiv, but can you show me you can do anything useful with it? Can you autonomously do this? You're just testing this and all that stuff. So yeah. So then Rocket 3 was born. And Rocket 3 was an autonomous mission. The idea was to give it a mission and or natural terrain. And then it would say, okay, go get that or pick up a sample, much like the tooth robot. So it's kind of like a tooth, but operating in a natural terrain. So let's see if this one loads. Okay, so I think there's something happened to this thing. Give me a second.
Payload, control methods, monitoring capabilities, and communications packages can be easily added or changed. This is Rocky 3,
Okay.
which combines.
So there was some glitchy thing there. Maybe you want to go back and try the other one too. Okay, let's try this.
E2B is the second of 4 rocker bogie-based robots constructed at JPL to date. Rocky 2B was used for more rigorous mobility tests in Death Valley, California, at test sites chosen for their similarity to Martian terrain. Rocky 2B is about 1.5 feet long and weighs approximately 20 kilograms. Although the robot is small, it can maneuver over almost any natural terrain. Those obstacles which it cannot climb, it can usually squeeze between.
So that's more testing. Hopefully.
E2B is the second of 4.
So then came Rocket 3, and here we wanted to give it a mission and say, go out there, get me a sample from there, and then bring it back. Right? So it's got an alarm, and then of course also so sees if it'll check if it's the right location and so on. This is really kind of a more contrived kind of a mission, and then we can go to the actual mission. So here, what it does is that there's something wrong with the way this thing works. So pause, resume, pause. Okay. It's working by itself, but I think with Zoom, it's having some problem.
So, Rajiv, very fascinating ones. I'm trying to get a feel of the tempo at which progress was being made.
Yeah.
So, what's the time period between Rocky 1, Rocky 2, Rocky 3, etc.?
Yeah. So in 1990, we had already built this.
Packages can be easily added or changed. This is Rocky 3, which combines the rocker bogie mobility system with behavior control software to produce the first robot in the world which performs tasks involving both autonomous navigation and manipulation in an outdoor natural terrain environment. Here, Rocky 3 performs a simulated sample acquisition and return mission to illustrate one possible application for planetary exploration. As with Tooth, the robot's computer and sensors are extremely simple and inexpensive. Nevertheless, the robust mechanics combined with the unique characteristics of behavior control make it one of the most reliable autonomous mobile robots in the world. Behavior control is based on a tight coupling of sensors to actuators through very simple reflex-like control mechanisms called behaviors. For example, when Rocky 3 encounters an obstacle which might be too big for it to drive over, it backs up and goes around it. Sensors on the rocker bogie mechanism warn the robot about potentially dangerous obstacles. Rocky 3 has about 10 of these simple behaviors, which work together to produce effective, reliable performance. Here, another behavior searches for soil which is soft enough to be scooped up by the robot's manipulator. The robot then returns home, following an infrared beacon.
Right. So you can see that we're kind of progressing from something indoor to outdoor to testing more of it, making sure this is going to work out. And then we have this, which is completely autonomously running outside. So all this is happening between summer of 1990 and by 1991, this is the version that you're seeing is 1991. And in fact, by 92, we already had our solution in hand. The mission was approved in 92, and basically in 93, we started working on the actual mission to Mars. So that's a pretty rapid process if you think about going to space, because typically missions were taking a decade. And that was the other sort of fallout of this, that we were doing things so fast that people were sort of scratching their heads and they used to think about missions in sort of spans of decades. And here we were building things in days, most of it because you learn later, it's a small team, 5, 6 people, building these robots again and again, same parts, just change the software, try this, try that. And basically that arm you see, I made it lathe in my, in our machine shop. Many of these parts still are around my house somewhere, that were broken and so on. And so I'm using home cameras and such to just capture these videos. But basically a lot of this was, wire wraps, handmill, very classic skunkworks word, right? And so progress was being made so rapidly that I think in a more traditional sort of environment, people were sort of wondering, God, I hope we're doing the right thing here because this does this really make sense? But it was making sense. And that is actually another fallout of a simple system that you can do so much so fast. Anyway, so Rocket 3 essentially demonstrated, and we did a lot of testing, of course.
All right, one quick question on the rocker bogies. I mean, it seems simple, but it seems like a very flexible platform to do things on. And was it capable of if incline sensors failed, or that if it became a dead bug, as I call it, with its on its back, would it flip itself over, or it was dead?
No, so rocker bogie is not designed to flip its, flip back up on. Like that's not the point. You shouldn't be able to do that.
Even with the arm, it can't push itself.
I mean, you can try, but if you look at the robot arms that are on the ones that are actually in the mission, very highly optimized for doing certain functions. They typically cannot push their own weight around. That's not to say that you won't try if that's where you got finally. And that's another advantage of having 6 wheels. Let's say one of the wheels was shot, like motor just stopped working. You have still 5 wheels to work with. In fact, depends on which wheel dies. So there are other reasons to have 6 wheels, by the way. So if there's 6 wheels, and if you sort of center it correctly, you can turn in place. You can actually just keep going in circles, right? You can just put all the other wheels at 45 degrees, plus minus, of course, and then you can rotate in place. So you can get out of very tight spots by just doing that, which you cannot do with 8 wheels or with 4 wheels. You can do that, but there are other problems.
What about sandy terrains or muddy terrains? Would it get stuck in those in their wheels? And
We'll come to that. So these are of course being tested in a very muddy terrain, but this also has rubber wheels. If you look at all the robots that have gone to Moon or to Mars, they actually have wheels that are used. They use kind of hollow wheels that actually have slats in them. So if the sand or something gets in, it falls when you go over it. So they don't actually collect anything. So yes, it can go over fairly sandy, and again, nothing is 100% proof, right? And so, yeah, of course, there are times you can get it stuck. But once again, because you have more than 1 wheel, 2 wheels, or 4 wheels, let's say that one side is getting stuck. You actually have so much traction because of the other 5 or other 4 or the 3, you can generally get your way out of there. Okay, so it's actually a fairly robust mechanism for going in and out of things. Good question there. Okay. Okay, well, the natural question comes. It's autonomous, you're doing things, that's great, but can you do anything useful with it? Because you don't want to go all the way there just to move around. You want to do something useful with it. Can the sensors the science can be small enough. And so actually the next question was, then look at these wheels. These wheels actually have these little holes on the side, and these are actually little grabbers. And so they really capture the sand. So they can go very well in sand, and they keep dropping sand out as the sand gets collected. So good question, Raju. So this was Rocky 4. Here we took all this autonomous piece and then added to it scientific instruments, real scientific instruments. You'll see that in the video now. And then you said, look, if we can pull this off, then I think we have basically a mission, a basically idea to go there. So let's look at that. And let's hope that this video works.
4 is the most advanced micromover developed at JPL to date. It is much the same as Rocky 3, but Rocky 4 carries functioning scientific instruments. Also, advanced construction techniques have reduced the mass to a mere 7 kilograms, even though the robot has the same footprint as the 20-kilogram Rocky 3. The robot's wheels are made of spring steel and are a prototype of a wheel which might someday be used in the frigid atmosphere of Mars, where rubber tires would turn brittle and shatter. Rocky 4 carries 2 functioning scientific micro-instruments. The first is a seismometer, which the robot deploys at an early stage in its mission. The second is a spectrometer, which the robot uses to determine the chemical makeup of rocks. The robot also carries a chipping tool, which it uses to strip off the weathering rind so that the spectrometer can view the unweathered material underneath. The small size and low cost of these robots make them suitable for potentially hazardous missions, and the autonomous capabilities provided by behavior control allow them to be.
So now we have a robot that's autonomous. It's lighter, it's like 7 kilograms. I think the one that went in space, about 8 kilograms, has real scientific instruments on it. It's an alpha scatter spectrometer, so you shoot either a laser or some kind of a thing that beats off the rind of a rock or something. So as you beat off the rind, you see the previous layer of whatever was in there. So you could go back in the history of that rock just by knocking on the rock. And as it scatters the molecules, your backscatter will tell you the chemical composition of what's there. And the seismometer is just a seismometer, and it was connected to the lander. So you drop it, and then just leave it there, and it sends the sensors information back to it. So that was just 2 simple sensors demo, so that you can actually do a very useful mission with a robot like that. And it's very small. It's like that big, about a couple of feet altogether, maybe 4.5 feet.
But Rajiv, it had
Yeah.
a tail. It was tethered somehow. What was the
No,
tail?
that tether was for the sensor. It got detached. You saw that. So that tether was for the sensor. So it brought the sensor out and dropped it on the ground. The robot was free of the tether.
So Rajiv, going back to Sanjay's previous question, so this was in the, again, 92, 93 timeframe or Rocky 4?
93.
Okay, great. Okay.
Yeah. So 93 summer was when the mission got approved. So it was early 92, late 92, 93. And then by this time, this mission is basically moving in a direction that says, if this really only costs, only weighs 7 kilograms, maybe we can strap it on top of something and take it somewhere.
So Rajiv,
yes.
I have a non-technical question. This is Rohit. What's the reaction of your management at this point? You're making progress at freaking unheard of speeds. And, what's the establishment doing through all of this?
Well, they're very unhappy, to tell you the truth. Remember, this is a kind of another battle going on. I think somebody wrote a whole article about it somewhere, but basically, I don't know if we have time for this or not, but when I joined JPL, I just kind of came to California and got interviewed at Caltech by 2 groups. And there was one group that had been doing robotics. They had 100 people or odd. It was called a systems group. And they'd been doing robotics work for better than a decade and even longer. And so they had the moon robot, all these things. These are people whose books I was reading, their articles I was reading, their journal papers I was reading. They were very, 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 very established scientists. And then there was another group. And this was a guy, his name was David Atkinson, and he had just started a group called the AI group. And he was also from University of Michigan, and he had come to my advisor and said, "Do you have anybody who can work in robotics and so on?" And so he said, "I'm assembling a group." So I was the third employee of that group. So I came back and they both interviewed me, and then they both offered a job. And as often say, you take the left turn when everybody takes right. I took the left turn. So I joined this group, and we were kind of like, we basically had very few constraints. I remember going to the place and says, "Where are the robots?" And says, "Well, you have to build them." And where's the lab? Well, we were looking for a room. Where's the funding? Well, we'll find it. And that's the world we were in. But it was the first AI group, which then grew to become AI and then robotic intelligence group. Eventually, I became the manager of all these things. But the idea was that we were kind of like these little, group in the corner that was trying all these things out. And for most part, in those situations, large organizations tend to just look away. It's like, "Yeah, those guys don't know what they're doing." There was a lot of sort of like, "I don't think they know what they're doing." And the only reason we were involved in the other one is because we were the AI group. So we had the planning algorithm for the other robot. They were doing the sensing, they were doing and these are my colleagues. I have very good friends there. And and I would have ended up in that group, but as a mechanical engineer, I actually belonged in that group more than I did in this group. But that was kind of the challenge. And so to your question, the reaction was mostly initially, I don't think these guys know what they're doing. I don't even know if this technology is going to work. How is this going to work over there? And how can you build a mission that basically can fail? So they continued the process that they were on, and their belief was that, hey, eventually these things will get faster, these things will get smaller, which is all true. We were looking at it and saying, I'll be 45 years old before this thing goes anywhere. So we were busy looking at this problem very differently. I think we also had very different types of people on our side. Like, we had basically I was the only sort of mechanical engineer there with some electrical engineering, robotics, background, some AI background, and the others were purely computer science guys. So it was very different build. So mostly we stayed out of radar. But by the time we had built Rocky 1, 2, 3, it was visible that this was a competitive problem. And by the time it was 4, it was decided that that's the way we were going to go. And then once the mission was approved, essentially the other side was, and then there was actually an effort made to, in fact, one quick thing I'll add to that. The other group basically said, well, robotics is not in their charter. They're supposed to do AI. So technically, if they do robotics, they belong to us. And there was actually a sort of
Attempted coup.
yeah, a hostile takeover attempted, and eventually that succeeded, by the way. They did acquire us. But sometimes you acquire a Borg, you become the Borg. So they acquired the wrong ones, I think. So anyway, we did eventually become that section, and actually the mission was done but there's nothing wrong. We're all scientists, and we figured out. But anyway, so good question, but a lot of history, it's more of a beer talk than it is a work talk. So Rocky 4 pretty much established the path. Here's an autonomous system, weighs almost nothing, does the job, and this paradigm really seems to make sense. So now, after 20, by this time, almost 10 years hiatus, no missions have gone, we finally seem to have something we can do. So let's move on to the real thing. This is just one part of the problem, right? This is just after you get there, what you're going to do. You still have to get there. So the next question was, how do you get there, right? We know, as you said, we already knew how to get out of the Earth. We knew how to sort of put things in on a trajectory. We sort of knew how to land something. So at this time, a whole bunch of new ideas came about and said, why do we have to land the traditional way? It weighs so little that maybe we can just drop it. Now imagine this, you build something, millions of dollars later, you put it together, and somebody comes with an idea and says, here's what I'm going to do. I'll show you something. Can you see this? I'm going to wrap it up in a little gift box. Okay. And I'm going to basically put this gift box together like that. And I'm going to throw it. I'm going to surround it with a lot of balloons and just bounce it. When it stops, I'll open it and there'll be a rover inside and walk away. How many managers will agree to that? So you're going to do this where you're going to put together something and put all this risk and then we risk it on this. And we said, why not? It's so light that we can actually do this. If this was 2 tons, we may not be able to slow down enough to actually do that. But if this is, so you might need rockets to slow down. But what if it's that light? Maybe we can do that. So a whole bunch of testing started. And so the real mission was then starting to design. So this is kind of the next part of this. So usually the way mission design works is that first part is where are we going, right? What is the interest? Have we not already covered this? Because we had 2 landers, the other people, by this time, there was a Russian lander also, I think. So we had some idea and we knew from the various orbiter, information that where things were, what we wanted to go after and also where would be meaningful to land. That big valley you see is the Valles Marineris, which is actually deeper than Grand Canyon. And it's a very interesting place, but you can imagine it's not necessarily easy to land in. So anyway, we went ahead and built this, so some mission scientists basically decide where you're going to go. And then, of course, you start working towards that. So the basic concept was we'll get there. We'll basically get into a circular orbit, and then we'll make an entry. It takes about 4 minutes to enter. In the next 2 minutes, we would start doing a parachute deployment. Then the heat shield would be in the front, so it'll burn off the heat shield and slow it down. You can see the speeds going down from 7,600 meters per second to 130 meters per second to 60 to 60 to 52 to and so on. At that point, you pop the balloon, a very large, very, very large parachute. This has an atmosphere. It's not as dense as ours, but it does have an atmosphere. So you just need a very, very large balloon because the density of the atmosphere is very low compared to here. And then you would slowly but definitely suspend this little package. Then it blows up with all the balloons around it. And then you knock off the top and the parachute and the top part flies away a little bit and falls on the ground or on Earth or on Mars. And then these inflated balloons would drop and they would bounce around about 30 to 100 meters, in that range. And they would bounce. Ultimately settle down. Then we'll deflate these balloons and then we'll open and the robot will come out. How many of you as managers would approve that?
So, Rajiv, another question. This one, a technical one. How many single points of failure in this whole exercise?
There are a few. Just a second, my dog's bark. Okay. There are technically in all these things, there are always going to be single points of failure. There are more than a couple hundred in this one. But obviously, you do your best to mitigate those, and you sometimes have backups and all that. But in the end, there's always going to be a critical path of failure, and surely you can. I mean, let's for example here it starts sensing. It's going back and forth. It's remember you're moving at what is it 65 meters per second, which is pretty fast. Okay,
Mm-hmm.
and at that point you are deploying this package that's going to basically dangle. What do you think happens when you're coming at 65 meters a second and deploy something? It's going to swing wildly. It's not just 7 kilograms of robot, it's also the lander and so on. So it's really more like 100 kilograms and there's stuff around it.
Wow.
So now it's swinging like hell, right? And you're going to use that to see how far down the surface is so that you can actually, point of failure, right? Then at some point you're going to say, okay, I'm not that far. I'm going to basically say 8 seconds. And remember, look at the time here, 32 seconds, 8 seconds, 4 seconds, 2 seconds. I mean, you can go wrong almost, what is a second? That's it, right? So yes, there's lots and lots of ways you can go wrong, but there are more ways you can go right. So you sort of have to, do this, with some faith, but there are in fact many single points of failure. And of course, any of these things can go wrong. So lots of testing, lots of reliability testing, and there's many very interesting parts of that. There is a little story I'll tell you. My much senior boss, the director of the lab, Dr. Edward Stone, we were standing after this mission had already happened and it was going to go. And he says, you have the easiest job in the world your stuff has to just work once because you just get the right, it's a robot, it's a robot. And I thought about it, I said, actually I have the hardest job in the world. It has to work the first time, And he looked at me and said, yeah, you're right, because there is no second time, right? This is it. There's no debugging it. There's nothing. It's gone. So yes, it only has to work once, but it has to work the first time. So there's a lot of really amazing, quality engineering that goes into this. They're very, very interesting methodologies that are deployed in this kind of a thing, and that's kind of another day. Okay, so this was designed as the mission concept. Lots of discussions happened, and ultimately it was decided this is the way it was going to be. So you'll see these images in the flow. So there is the drop from a helicopter to see how it would work when you're coming in at a certain speed. That's ground is somewhere here in California, and we're dropping this thing and to check how it be. Now remember, we have different gravity here, but basic idea is the same. On the right now you see this bouncing ball. Inside is the rover, thing. On the bottom here, you see the rover moving slowly off of a deflated balloon, and this thing opened up like this. So these are all little tests that are done many, 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 many times, and to find all these little, as you said, failure points. And finally, when this is done, you'll see this on the right here, where it'll start deploying the alpha scatter, basically a spectrometer. Okay, so these are all basically mission concept tests and trying to see if this really makes sense. And once that thing gets, you can see this thing's getting deployed, it will sort of jam it into the ground, and then it can do some analysis. You can go to it on the rock. So most of the time, these things are very purpose-built with very specific use cases. So that was just one type of test. Okay, so each team then goes and does its own part and tries to figure out, that what are the failure points, how we can best compensate. One very interesting failure compensation was, all right, so you land, you've deflated the bags, but the bags are all over the place. And you'll see later on when I show you a picture, what if the bag is over one side and you thought you were going to get off on that side? Okay, so eventually the spacecraft that went actually had ramps on both sides, because we figured if one side was blocked, maybe we can open the ramp on the other side. And that's exactly what was needed, because these balloons are not necessarily going to deflate some systematic way. What you do is you deflate the balloons and then you retract them. So that process is not perfect. So we ended up having this kind of a ramp on both sides. So if left doesn't work, we'll go to the right. So now it's final assembly time. That's what it looked like on the assembly, platform. It was flattened. There are actually 2 or 4 actually hooks underneath that hold it. They're basically, think of it like rubber bands that are holding, not rubber band, but and then somebody cuts it. So there's a little trigger that's shot from here. And once you do that, it fires off these little, almost like an explosive, and then burns it off, and boop, it pops up. So during the journey, the spacecraft is compressed and then it stands up. And this kind of a final wiring inside that pyramid, inside this thing here, and they're wiring it up. They close it, and they put it upside down inside the cone. And this is actually the heat shield here, and their inside is the cone. And then that's all assembled on top of a rocket cone, and then that's where that is. And that's a Delta rocket, and that's Moth Pathfinder. So it's time to go. Everybody's got their hands off of it, and then you'll kiss it bye, and then goes. And so on December 6, 1996, it went off. And of course, this is a deep space mission, so you actually have to break away. You need a certain amount of energy and velocity to get out. And so then we assume that that's what happened when we got to the surface, and then it's probably what happened because we have no way of validating this except from sensor data later on. And so it opened up like that, and of course these balloons were underneath, and then finally it ramps on both sides, but it picked one ramp and got out, and eventually it was on surface. And then July 4, 1997, there it is. And look at the balloon on left side. right side rather, that ramp couldn't have been opened because it was in the way. Right, so the ramp on the other side opened and we got off. And that's a flat thing, and I finally stood up. That was the very first image that came back. Now I was talking about the bandwidth issue, right? So even after you land there, everything is settled down. You finally open, you do all these things on your own, and then you take a picture. The first bit will get there in 20 minutes, but the whole image will take a while because it's a lot of stuff. And then of course you only have 8 minutes whenever the opportunity shows up. So then you send it to the orbiter, then orbiter holds, gets it and sends it off through a direct link to Earth. But your link to the orbiter shows up when it shows up. So there are other points of failure too. What if your antenna mast didn't open? What if your antenna mast didn't connect? If it connects, it may happen that it's pointing the wrong direction, or it's usually a straight mast, but if it's not. So there are so many ways this thing can go wrong that it's almost like, there's a lot to think about. Okay. So those are the first pictures of the robot on deployed and running around, and moving around the rocks. There's really no good videos because in those days we really didn't have good imaging. These are all very low resolution type of things in today's resolution sense. But these are images that came from the robot. And this is the image of the lander looking at from the rover. There's a little camera inside and it's looking back at the rover, and you see how it got deployed. And these images come in pieces, so you have to assemble them. And you can see the kind of terrain that we landed into. You can see the little sort of marks on the ground that show where all it went and finally got to where it is. And you can see how the balloon also is sitting around it. So one side is pretty much still up there. And so luckily we had the other path out. So that's us, the 5 guys. There were other people. Of course, this mission takes many people, hundreds of people. It's not like, but this is the rover team. That's of course that's Iran Ghat, that's me, that's John Locke, that's Ran Fan, and Robert Ulev. And there's another guy who's taking the pictures. We should have been there, but anyway, David Miller. And there were other people too. But back in what you see in the back there, that little thing with the round foot is actually a model of Viking. And this is so we kind of celebrate a little bit before when the mission got approved. This is not when we landed by the time everything was disassembled. Okay, so that's our team. And so, I made a bold statement. I said, well, this is a momentous occasion. There was like no mission like it before and totally changed everything. And of course, I need to justify that. So Jonah went in 1997 based on all these things that you saw. These are all the missions that followed. Spirit in 2004 lasted for about 6 years. Opportunity lasted for 14 years. Curiosity is still going after 12 years. Perseverance just landed, and Perseverance actually has a helicopter on it, which is another mode of transport. And of course, you can see the size is also getting bigger. If you look at this guy here standing next to it, it's a lot bigger than the 7-kilogram robot we sent. But not only did it have impact on the US program, this is the Chinese program. U-21, we went to the moon. It's also basically the same mechanism, same kind of robot. U-22, which is also exactly a copy of basically our robot in 19. And in Zhurong, which is actually also went to Mars, is their first landing on Mars, successful landing on Mars, is also basically looks very much like ours because the same mechanism. So pretty much the standard is rocker bogie based design, behavior control, and essentially this kind of mission concept. And even Pragyan 2023 was actually the same. If you look at that, they also use the same exact mechanism. So every robot that has come since essentially looks like that. It's like a car with 4 wheels. I mean, there's not a whole lot of other options. And so if you look at how this one mission had an impact, Viking 1 and 2 happened back here. Almost 20-some years later, we finally returned back with Mars Pathfinder. And now look at all the activity that's going on. And there's many more planned. They're likely to be maybe 20, 25 missions in the next decade. Now, remember, we can only go there every other year. So the Chinese, certainly Russians, Americans, Europeans, India, certainly other countries, the Middle East is trying, they already have an orbiter now. So this totally kind of opened the floodgates. And so that's kind of the story. So thank you. Questions?
So Rajiv, fantastic talk. I really learned a lot and great work. Just a quick question on the Pragyan. Does it only have 4 wheels? Does it have a
Yes.
rocker bogie
It has,
mechanism
I
or?
think it has 6. There's a wheel that's up there. It's a little black wheel. If you look at, let me see. There's a little wheel up here. I think. I'm not sure, but it's basically got that kind of a, what they call asymmetric rocker. Yeah.
Cool.
So Rajiv, great talk. I mean, more of a general question. I mean, it's really a 3-part question. So in your view, I mean, what is the time scale, say, for a sample return from Mars? And then related to, I mean, humans habitating Moon, so that it'll be a stepping stone to Mars. So how soon do you expect that is going to be happening? I mean, it's like a permanent base, like in Antarctica. And then third part is, how soon do you think we would go to Mars? I mean, humans in Mars. I mean, at least step foot on the Mars. So it's a 3-part question.
So there is not a good answer to any of those because we thought we would be already doing Mars sample return. But, Mars sample return is not difficult simply because, of obvious reasons. But think about it. You have to send something and then to launch back from there to come to Earth. I mean, launching from here to go out of this planet is pretty hard, right? So now think about it, you got to set up mechanism there so it actually takes off. And it's not a small planet, it's not like you can just get off like Moon, So it's a difficult proposition. And I think we have many concepts for that. And the original expectation was that we would have a Mars sample return by 2028. That was a revision from 2004, by the way. It was supposed to be in the first decade of this century, this millennium, but then that was revised to 28, and now they're thinking 2040. And then last week, if you saw, there was a budget that was proposed for $11 billion, and then basically NASA said, no, we're just going to go private on this one. So that's one story. There are others who, who say, it's not that hard, So for example, Elon Musk keeps talking about going to Mars like that, and by 2030 and so on. I think it's unrealistic. Not because it can't be done. It can be, but where's the for a private company? Where is the economic justification? To go to Mars. It's not like there's uranium or oil or something that you can economically bring back to the Earth or do something with it. It's purely for science, right? So who's
Rajiv, would sample returns be easier from maybe some moons of Jupiter because they're smaller?
But there is the other problem of going to Jupiter. So yeah,
Or going forward?
so there are already missions planned to go to Europa, and other Europa is probably the most likely moon will be. In fact, it's already planned to go there. But Amresh, the problem to go in going to these places is that it takes very long time to go, and again, that's a whole another chapter. Like, I mean, we don't know how it's going to be on Europa. It's, we sort of know what Europa looks like based on Galileo mission, which went to Jupiter. So we have very good understanding of, we've discovered all these moons, there's 90 some moons on the Jupiter has. Europa seems to have an ocean, probably very cold. So, and there are some others that Io has some volcanoes. So, those bodies might be, and they have hard surface, not like Jupiter, which is a ball of gas. So we are looking at other places to go, but that's only further. So I think more likely sequence is going to be that you'll first go to the moon, establish probably some sort of an outpost. I think that, whether anybody admits it or not, I think that while science is certainly the one objective, I think military is the other objective. Also occupying things, is always an objective. So I have a feeling that we'll probably stabilize the the things like space station and others, and of course, a kind of a station on the moon first. Somebody just
So you
recently
think that could happen in, say, mid 30s or?
mid-30s, I think we should probably, I think because I this is just my theory, okay? Don't,
Sure.
okay. This is just my feeling that I think what's going to happen is that China is so determined. India also quite determined, but different resources. And I think that China, because of its momentum, will continue to move very rapidly, which will probably light fire here, and will probably start competing like we did before, right? And so we'll start spending money, and because what we don't want is, at least that's the general perception, that we don't, unlike today, we work with Russia every day, right? I mean, all our astronauts are launched by Russian spacecrafts. We deliver food to each other. So to Chinese, it's not like that. We compete with each other, and there's actually a military motive in any rocket that can go this way can also go this way. So all these technology developments that come out of this can technically be military usage also. So I think that what will happen is that this competition will get more fierce. Okay, and at that point, unless some kind of cooperation evolves, I have a feeling that what will happen is that you make one, I'll make one. You make one, I'll make one. And that'll probably speed up as it did in case in 60s and 70s with Russians. And that space war or space race or whatever you call it will eventually probably yield some momentum. And then it goes where it goes. The private side will also evolve. It's what is beginning to happen is that, as I said, back in 90s, your launch cost was reaching 50, 60,000 dollars per kilogram. Today, you can launch for about $2,000 a kilogram, on a commercial rocket, right? And the goal is to keep bringing this down to possibly, a quarter of that. And so at that point, it'll be possible for even folks like us to jump on a quick ride around the earth or something, so I mean, just way less, and that'll be better. So I think the idea there would be that those progresses also make these more reliable and make it easier to build things that are cheaper and basically support more missions in the future. I don't think I mean, there's just no economic motive today to send a human all the way to Mars. It would, we haven't even figured out how to bring the robots back or
Yeah.
bring samples back. And I mean, unless it's a one-way mission, which is obviously that's not an option. But I think that the idea being that the only way you can really get there is to actually have all these steps figured out, and we haven't figured them out yet. So I don't think it's realistic, but things can be. I mean, nobody thought this was going to go in '96 either, but it did, right? So I completely think that something could whack your head on the side, and something else could come up tomorrow, which makes it go faster. And yeah,
Thanks,
Hey,
Rajiv.
Saurabh, back then you landed this on a balloon that bounced and came to rest.
Yeah.
Is that how you're landing them even now?
No. So as they got bigger, they got heavier. And what was taking 8 seconds to come down will now take a lot less time to come down, and you don't have enough time, and you have different kind of dynamics at play. So all of the more recent, there's still the standard. Almost any time you enter an atmosphere, you're going to need some kind of a heat shield. So the first phase is more or less the same. You have this heat shield that's in front of you that melts down as you're moving, so you don't burn down the spacecraft. And it slows you down enough, and then it gets removed. Then, because it has atmosphere, you probably want to use some kind of aero braking. So you pop a big parachute that slows you down even further. That's usually the best. And then, of course, you use retro rockets to push you back. Most of the, not most, almost all of the new missions are quite large. They're very, very big robots. If you look at this guy is going under the wheel, he's almost, look at that size of that guy, look at the size of this guy. Same thing with the robots that the Chinese are sending. They're pretty large. So what you do is you come to a certain spot, and then you use a kind of a crane. That's what they use for Perseverance They use a crane that lowered it, the robot. Boom. And there's no lander because these robots are going to go thousands of kilometers. When you've got 10, 12, 14 years, you're going to go far, right? That's also the other argument, right? I mean, you don't want to keep building really small things. I mean, if you build something that's that big, it'll take years to cover. Dog. It'll take years to get somewhere. So you need larger vehicles to go larger distances.
Hey, Rajiv, Bharat here.
Hey, but
Yeah. Firstly, very awe-inspiring what you've been doing, felt a part of history. What you achieved 15 years after passing out from the institute, I think is really great there. And I didn't know that you were a part of history, literally a part of history there.
good,
I
man.
learned
Old.
new. Yeah. Just wanted to understand, after the 96, 97, what really happened? Did I know you moved out of NASA, right? You moved out of NASA around that time, and how did it move ahead, or is it just that the budgeting and the funds stopped at NASA, and hence they didn't move ahead in Mars to that extent?
So, we are always subject to budgets from the Congress. And sometimes, we as engineers and probably just generally interested in science think, what's a couple of $1 billion when you're spending $1 trillion on something and hundreds of billions of dollars? What is $10 billion, $15 billion for the US? But the reality is that there are other walls that appear when you do missions, in my opinion. Just like there was a wall after Viking saying, okay, so, unless we have an autonomous solution, there's no point in just going there and putting. And while that was going on, there were other ideas being considered. Why don't we just send something with like 100 penetrators, right? So we'll drop them all over the planet so we have 100 data points, right? That's one way to do it. So you have 100 spots, but you have 100 data sets, right? So until we figure out how to go with robots. But then there are other things like, do you want to really pollute another place like that? And is it justifiable in so many ways? So I think first you hit these walls. Other priorities show up, right? Why are we just going to Mars? Why are we doing Moon? And is there really not other science that we need to look at? So, James Webb was being built. Absolutely great mission. Took a long time, right? It was very much over budget and over schedule. But it was necessary to do because Hubble was basically not gonna, he's already 30 years old. And so I think what starts happening is that you got this limited budget and your priorities start shifting, and there's sort of sameness to certain things, right? You go once, you go twice, you go thrice. People don't even pay attention to it. What happened to Apollo, right? Apollo 11, wow, even before that, 12, 13, 14, 15. I mean, we don't even know or remember the names of astronauts that went on, the latter missions, right? So the point is that I think as organizations, you start sort of moving your priorities to other options that emerge. You move your priorities to things that maybe have greater yield, and also, I think sometimes I feel it's kind of a little bit myopic, here in US. We don't set these 20, 30, 40, 100-year long goals here because of, politics, the way it works. And so what happens is that we don't work at the horizons like we used to. We don't make programs that are looking well out there. Our idea was, hey, once we put this, we've shown that it's really quite cheap to get there. That mission cost $150 million. The majority of the cost was launch cost, right? And of course, the ground cost. And so if you think about that, for $1.5 billion, you could do 10 of those missions. And if anything, it would have gotten cheaper over time, right? But we didn't do that. And we could have done that every 2 years, but we didn't. We did only 4 more missions. But partly it was also that, how do you consistently fund something? So I think what happens is these priorities cloud things. We don't make, 100-year plans and commit to it. But the time horizons for space have to be at least 2, 3 decades out, if not, 50, 60 years, 70 years, 100 years. There has to be out well into the next 2, 3 generations. And unfortunately, with the kind of politics we have, it's hard to do. It's much easier for the Chinese or the Russians to do that compared to us. And that's I think partly why you see these missions not getting renewed, or having that commitment that whatever happens, we're going to stay with it.
Question is, doesn't Mars have a lot of natural resources which can be used for humans?
So I think even if it does, the cost of actually transporting them here would not make sense, right? I think that more likely than not, at this time, the primary interest in Mars or even Europa, as I think Amrish was mentioning, like going to Jupiter or places, really from a science perspective, we just want to know about, Mars seemed to have had rivers, had flowing rivers, oceans. But where did they all go? Right? What happened to the atmosphere? Is this something that we are headed for? Right? Maybe it's 2 million years away. Maybe it's 20 years away. We don't know. Right? So what happened? And it seems like a lot of the atmosphere escaped. Maybe there was a big meteorite that hit, and then. So I think right now we're also looking at, is there life there? Because that can completely change our own view of ourselves and many other things. So I think today nobody's really thinking about in terms of economic returns. I think we are primarily looking at it as a science return and building platform to potentially someday becoming a spacefaring, routine spacefaring species. And we're not quite there yet, So
Rajiv,
yeah.
quick question for you.
Yeah.
As I see the slide up there with the other countries like the Zhurong and the U2 and the Pragyan, just curiosity, have you ever been in contact or know of the people involved there, or have they ever been in touch with you or something? And how would that reaction be? This is a human interest question.
Well, I don't know.
I mean, they're copying your design, basically, right? In a sense.
Look, it's not like these patents have run out a long time ago.
Yeah, sure.
No, so that's not and if you look at how NASA was established and how NASA sort of works even now, is we publish all our data. In fact, we give real-time data links to the data that comes from Mars. The whole mindset is that we share with the humanity. This is not for our country. Now, there are things that we do, obviously, we don't share. There's a lot of military missions that I worked on a few things, and we obviously don't give those out. But I think for most part, it's science. Now, China doesn't necessarily do that. China hasn't shared, for example, whatever it is that they've found with Zhurong or U2. They generally give, in fact, it's hard to even get a picture of the robot. We had to do some digging to get that. Even India doesn't do a really good job of that. I think it's just, US is different. You've been here like me, and all of us are here. And, the attitude towards science is very different. I'll give you a very simple sort of mindset difference. And I actually have met with Chinese and also had some contact with Indians. So if you think about how US looked at it, is in a competitive spirit, right? It was like, oh, I can't let Russians get ahead of us. That's kind of how our space program grew. It was really part of Air Force, and then became a separate organization called NASA, but it was really part of Air Force. In fact, most of the stuff there is basically Air Force. And so most of our scientists that we had when these organizations were established came from Germany after World War II, right? So Dr. von Karman, who was basically a professor here and was the propulsion guy who led this jet propulsion labs, and then the Russians got some and we got some, and that's how the space programs got started. We didn't have much before that. The Germans were heading that stuff much more. But our attitude has been always been to share because it's for the broader good. It's not like we are kind of one as a species and we're going to another planet, and that's kind of a very defining aspect of our science here. Our scientists publish papers. Everything we find, we publish, we share. We hope that people can build upon that and then go and maybe we'll all get there as a species, and learn things because that's really what science is. And as I said, in a meaningful horizon, we're only going there for science. It's not like we're going to go but I think some of the others are now looking at as what we were looking at with Russians. It's kind of a competitive thing for Chinese right now. We want to go as. And there's another thing that this missions do. The 60s push for going out there produced so many scientists and engineers in this country. The STEM was like the standard thing. Everybody had to do that. Like, you got to be good at math. You got to do this. And you didn't have to talk about it. Everybody wanted to be. I mean, rocket science was like, wow. I mean, it was like brain surgeons and rocket scientists. That was it. So we produced enormously successful engineering and organizations and all that. Basically came out of this, this kind of a leading mission out there. To some extent, what China and India are probably trying to do is the same thing. And we probably need to do that again over here because what it does, it just brightens their eyes. I mean, I've done these kinds of much other versions of this kind of presentation with children from when my kids were in kindergarten and many times after that. And I cannot tell you how it just like, wow, robot, Mars, it just changed everything. So our approach has always been public facing, not so much from them. With Chinese, I've had some presentations like this in the early days, but of late, I think because of Department of Commerce and all that, you have to be careful what you say and do. I mean, this stuff is old anyway. Indian, I think we are good. We cooperate with them. I think I'm not involved, but I think we cooperate with them.
So Rajiv, I'm not sure if Saurabh is moderating this or not, but maybe if you want to stop share screen now, we can all see each other. And there's one comment from BS in the chat, and I think Jacob had his hand up. So
Yeah, go ahead, Jake.
Yeah, can I ask a question? Rajiv, great presentation. Maybe three questions, right? Just so I can ask all of this. It'd be great to chat. One, where are you now? Just trying to, I read some of your bio on the IITK page, but where are you now? I'd like to know that. Second, 86, January 86, when that space shuttle blew up, what were your thoughts, right? And is that a preventable item? And then third question is really about I mean, do you have kids who have been involved with like middle school robotics, high school robotics? I mean, I see a lot of that happening now. Just is curious if you're involved with that, with any of those activities.
Yeah. So what am I doing now? I don't really know what I'm doing now. So I think I left in 97 because of, I mean, you go once, you go twice, the same thing, and I actually worked a little bit after during the mission but I was also working with the military a little bit. And we had started this kind of a, nascent robotics company. And so my mind had turned towards, building something that was going to be more, more in the commercial space. So I worked with lots of robotics, use cases for the next almost, I want to say 5-6 years. Built robots that were autonomous for, I worked with Japanese a lot, and they were much more advanced. We were looking at micro machines, very tiny robots that go inside pipes, around pipes, inspections, all that kind of stuff. So this is late 90s after I left, and also robots for moving containers on ports. Kobe port uses one of our, so with Mitsubishi and other big companies. So basically applying these technologies in more commercial space is where I thought I was going to go. I think much of what you see in robotics today wasn't possible because we didn't have the compute for it. AI as we know it today really would have been hard to pull off without the kind of compute we have today. So for most part, that's really what we did. I had a lot of non-competes and stuff from various earlier things. So and then I kind of moved my attention towards applying forms of technology to different problems. And now, I still have great connections. I still take a lot of interest in these things, and I'm very connected with the community. But I started company. There's a couple of companies, but basically focused on embedded systems. We produced the first embedded kernel embedded system which has multiple kernels. So a kernel for real time and a kernel for doing your sort of second-tier processing, and that allows you to build a real-time system that can be used in a phone, but it can also be used in very fast-moving things that also require decision making. So still stayed in the embedded world for a few years, and then I got into what I do now, where we have built platforms that allow you to solve very typical sort of technology problems for social problems. So we work with homelessness, housing, fire prevention, and so very different from robotics in some ways. But basically, the hard problems to solve, they're not that easy. So it's really solutioning more than it is anything else. And so we've made some really many firsts in those directions too. It's another time, another day. But yeah, so most of the activity today is that. I am connected with some people in India, especially IIT Kanpur now has a newly formed department for astronomy and space exploration. So I'm kind of connected with them as well. And yeah, I take normal interest and sort of stay connected with the community.
Rajiv, just one question.
Yes, sir.
Pankaj here.
Yeah.
When you sent this rover to Mars, one was the software updatable subsequently, and second, was the software updated, and if so, why was it required to update it?
Yeah. So always, you build these things with the idea that you'll have to change it. And there are countless reasons for it. It could be you have found a bug, but which in a complex software is not unusual. But also because think about it, if your spans are going to be years, technology will change, right? Your objectives may change. So almost every system that ever leaves has a lot of upgradability or sort of modifications possible. And so, in fact, best example of that is Voyager, which last 4 or 5 decades back, and Voyager 1 and 2 both are out of the solar system, and we are constantly modifying the software on those so they can talk back to us because they were not designed to go past the solar system, let alone where they are now. So we always make systems that you can modify software because hardware could fail and you have to kind of make adjustments for that. And so that adaptability is there. Now, the mission that we sent was supposed to last only 30 days because remember, it's called Pathfinder mission. The idea was, can we really get there and do something useful? And so it was only planned for 30 days. It lasted 79 days and then it died. There was no expectation of it to go much further. Did we make some software adjustments? Yes. There were software updates sent out even during the trip and then later because we discovered things that when you get there, you almost always find out things you didn't expect, right? So you have the sort of way of updating, kind of like your printer updates its software by itself over the internet. There's some sort of process like that. So yeah, we did, but no major behavioral changes were made from here. But almost all the missions that I talked of later, they're all 6, 7, 8, 10 years into their programs. Yeah, they make updates all the time.
Okay, thanks for the update.
I see Jai has his hand up.
Hi.
Thanks for the lightning talk, Rajiv, and thanks, Saurabh, for inviting me to the to the chat. So, Rajiv, you said that there are not as many rare earth metals that we have yet found proof of on Mars when it comes to privatizing the travel or exploration in a much faster timeline as compared to 10 to 20 years, as you said, as you assume it will take. So around that, like my guess is that the next like how it's going to happen is more than curiosity. Probably it will be promoted more by consumerism and capitalism, because what we saw with the whole NFT boom, where people were paying crazy amounts just for pictures of rocks, not even real rocks for that matter, right? And so like it's just to have like a sort of like title where I have some real estate on Mars, probably would be a good way that Musk is able to push this timeline of 10 to 20 years and compress it into a few years. Like, what do you feel about that?
Oh, why wait that long? I'll sell you a piece of land on Mars right now. So we don't have to wait very long at all. If you got a couple of dollars, send it my way, and I'll send you a certificate. The point is that think about it. It's taken us 50, 60 years to reduce the cost of launching from Earth into deep space from what was probably equivalent of, in today's dollars, probably worth $200,000, 300,000, or even $1 million a kilogram to like $2,000 a kilogram, right? Now imagine bringing something back from there, right? We don't even know how to install anything. We have nothing there right now, so we are still figuring it out. Again, maybe there could be a completely, out of the box technology that solves that. But today, there's no economic model that makes sense today. Yes, there are ideas like, NFT, as you said. People have tried to sell stars. They'll name a star for you. And that's a pretty silly idea if you think about it, because you can do it yourself. There is no reason to go to somebody to mark you, because all you do is buy a telescope and maybe pick a number and look there. Whatever you find is yours, and who cares? So I think NFTs are not really doing that great anymore, are they? Now that you can generate,
Hey, Trump's ones are doing great.
Yeah, the Trump ones are doing great. So the point is that I think these are short-term concepts. It's very hard to create a true economic advantage without, there's no sustainable conversation yet. I'm not saying that it's not possible. People have tried tourism. Look at what happened to Virgin Galactica. Gone, right? I'm sorry, Trump, but Elon Musk has talked about that you saw Jeff Bezos launch a company for they're not doing that great. It's only $250,000, really. It's not that much money. If you think about it, to take a spin around the earth, $250,000. I said to people 20 years ago that two things, just don't die soon, and the other is keep $250,000 in a pocket. You'll be able to take a spin around the earth by the time you get 60, 70, 80, something like that. You can do that today. $250,000 will get you a spin around the earth, but I don't see many people signing up. So I think it's really hard to use tourism and such until it becomes a routine process, and that's going to take some time. I just don't see that taking off, and without huge government subsidies for decades to make that pathway really easy. And then, of course, people will jump into, like any technology. So, but I think hope's alive.
And Rajiv, how about Mars acting kind of as a base station for mining in the on the belt, right? And would that logistical advantage be you think might be significant enough?
Yeah. So first, let's do the moon, right? Let's get that going. as a starting point, because the escape velocity and the cost is much lower from the moon than from the Earth. So first establishing a base on the moon would be a starting point if that happens. Mars, yeah, it could also be one, but with these things sort of moving around, some point I think, yeah, I mean, I'm generally optimistic that over a long period of time, maybe in our lifetimes, but maybe beyond, there will be these stations. But there is a really interesting book that I read 25 years ago that said that if you're that good that you can actually stay on a land and you can launch things, and kind of like what you see in all these sci-fi movies, why wouldn't you just live on a platform that floats all over the solar system? Like, why would you just not be moving around all the time and be in like a little moving planet of your own? Why would you actually want to stay in one place? Yeah, you visit these places, but by and large, you become like a moving object of your own self. You could build like a little city that roams around. So I think if you got that good, I would suspect that option might also show up as a very valid option that says, why stay in one place when you can have platforms all over the place? But I think in progression, it'll be something like, that's why we created the space station and other things. We'll have some structures around our own planet that allow us to quickly get on and off, and then eventually something on the moon, and then eventually to some other places too that'll sort of serve as the way stations to wherever we want to go. But what's the timeline for that? I don't know. I mean, probably, I think no less than 5 decades, I would say.
Great. So that's almost 2 hours now. Maybe we should end this here.
Yeah, sure.
Yeah, thanks a lot, Rajiv.
Thank you.
Excellent
This was
talk.
wonderful.
Thank
Thanks,
you.
And
Yeah.
I think a lot of people have already said that, so I won't repeat that it was wonderful. That I did. Okay.
It's a pleasure.
So bye. Good night, everyone.
Good night, everybody.
See
Good
you
night.
Yeah,
next
bye everyone.
Saturday.
Have a great weekend.
Thanks.
Rest of the weekend. Bye.
Thanks, Rajiv.
See
Thank you.
Thanks.
No, Saturday, 18th May is the next stop. I'll just announce that. Thanks.
Bye-bye.